Dear students, I now give a small lecture about the remaining part covering the provable version of the Goodstein sequences. We will speak about the provable versions of the phase transition for the Goodstein sequences. I start with some lemmas. They are of technical nature and they will be used in the future. Lemma 1. If alpha is big enough, then we get the following, namely that h alpha of m plus 1 at least as big as 2 to the h alpha of m. How can we prove this? By induction on alpha. Well, the induction step is easy, but the induction start is somehow interesting. So we start induction with alpha equal to omega to the omega. And then obtain the following. H alpha of m plus 1 is h omega to the m plus 2 of m plus 2, which is the same as h omega to the m plus 1 times m plus 3 of m plus 3. On the other hand, we obtain, so this is the same as h omega to the m plus 1, m plus 3 times iterated applied to m plus 3. Now h alpha of m is the same as h omega to the m plus 1 of m plus 1. Clearly, this one is much smaller than this one. Now, I claim that 2 to the h alpha of m is smaller than h omega to the m plus 1 of h omega m plus 1 of m, which is smaller than h alpha m plus 1. Why is this the case? Well, what do we need is that h omega to the m plus 1 well, I do slightly different. I plug in here m plus 2 or m plus 1. But this one here, well, here we have the exponent m plus 3, here have m plus 1. So it's the exponent m plus 2, and this argument m is smaller than m plus 1. So h omega m plus 1 is bigger than h omega of m, because m is at least as big as 0. And this is h m plus 1 of m plus 1. So what is this? Is basically 2m plus 2. This means that if I iterate this function here, this function m plus 1 many times, I iterate the 2 times function. So after this clearly means that h omega m plus 1, let's say n times iterated applied to, let's say, maybe m times iterated applied to an arbitrary argument n is at least as big as this 2n plus 2, 2n plus 2 iterated is bigger than 2 to the n, 2 to the m. I see. Well, this bound is true even for n equal to 0, because here is 2m plus 2. Let's see, is this correct? No, for m equal to 0. Well, let's assume that m is at least is equal to 1. And then anyway, we have this estimate. And from this estimate, we can use here an exponential function of this number. This is bounded by this number. Note that here we use m plus 1. And so we see that this number here is the number we want to bound. This number is at least the exponential function, so that's fine. Now, if alpha is a limit, then it's trivial. H lambda of m is the same as h plus 1, is the same as h lambda m plus 1 of m plus 2. By induction hypothesis bigger than 2, h lambda m plus 1 of m plus 1, which is bigger than 2 to the h lambda m of m plus 1 by the Bachmann property. This 2 to the h lambda of m. So lambda m is smaller than lambda m plus 1. Therefore, stepping down along 0 is possible, and we get this inequality. And if alpha is of the form beta plus 1, then h alpha of m is the same as h alpha of m plus 1 is the same as h beta of m plus 2. Induction upper is bigger than 2 to the h beta m plus 1, which is 2 to the h alpha of m. I see. And now, once we have this lemma, we see can also make this stronger, namely lemma two if alpha is at least as big as omega to the omega. Let's say m is at least as big as 2, and then h alpha of m is h alpha of m plus 1 is bigger than 2 index h alpha m. So tau of 2s by h alpha of m. The proof, just the same. By induction on alpha, the limit step and the successor step are fine. And what can we say about h omega m plus h. You have to estimate h omega m plus 1, m plus 3 of m plus 3. So that's a term which you obtain here. Now we show this is bigger than, well, again, this is bigger than 2 index h omega to the m plus 1 of m. Because plus 1. This is a term which we need here. This was because h omega square of n is so what do we have here? We have here this function iterated m plus 3 many times. If you can show that this function here is permeating the exponential function, then here we have an iterate of the exponential function. So we get here an iterate. M plus 2 case iterate of the exponential function. Aha. That's maybe not yet enough. So let us consider a new page. So h omega to the omega of m plus 1. This is h omega to the m plus 1 of m plus 2. This was m plus 2 here. Was h omega m plus 1 of m plus 3 of m plus 3 that we already have seen. So that's the same as h omega m times h omega m plus 1 m plus 2 of m plus 3 of h omega to the m plus 1 m plus 3 m plus 3. Why is this the case? We take here the fundamental sequence and plug in here the m plus 2 iterations in the argument. Aha. So this is the same as h omega m plus 1 m plus 2 many iterates of m plus 3 of h omega to the m plus 1 m plus 3 of m plus 3. Now I need that h omega m of n grows at least as quick as the exponential function. So for this, I need that argument m is at least as big as 2, because h omega square of n is h omega times n plus 1 of n plus 1. That's h omega n plus 1 of n. And this is here an iterate, n plus 1's iterate of the function n goes to 2 times m plus 2. So this is at least, this is strictly bigger than 2 to the n. Okay. So this function is an exponential function iterated so often. So this is bigger than 2 index h omega m plus 1, m plus 2, m plus 3. And this is bigger than 2 h omega to the omega of m. Aha, that's interesting, but was a problem which was fixable. Need another technical lemma, which I already used for the Hydra battle. K and n are bigger than 0, then 2n k of 1 is less than equal to 2n plus 2k minus 1, where this notation here means a 0 of b is b, and a l plus 1 of b is a to the a l of b. So we have here an iterated exponential, k times iterated exponential of another n times iterated exponential. This can be resolved into one exponential, and surprisingly, this grows not too quickly. The reason is the type of bracketing. Proof. Well, if k equals to 1, so we do induction on k equals to 1, 2n 1 of 1 is 2n, the same as 2n minus 2, 1 minus 1, so that's fine. K goes to k plus 1. Well, it's somehow easy, but one has to be careful with the estimates. So we start with this term. So that's nothing else than 2n to the 2n k of 1. Bounded by induction hypothesis by 2n, and then exponent we have 2n plus 2k minus 1. Now, if n equals to 1, the claim which you want to show is already trivially true. 2k of 1 is 2k bounded by 2n plus 2k minus 1. Since k was bigger than 0. So we assume that n is bigger than 1. Why do we do so? Because we now go into the definition. So 2, this is star. Star is bounded by 2 to 2n minus 1, 2n plus 2k minus 1. This is the same as 2n minus 1 times 2n plus 2k minus 1. Now this is the same as 2 to the 2n minus 2 plus 2 index n plus 2k minus 1 minus 1. Now this term here is bigger than this term here, because here we have an n minus 2 involved. K is bigger than 0. So this is bounded by 2 to the 2 times 2n plus 2 k minus 1 minus 1. This is bounded by 2 to 2n plus 2k minus 1. So by the exponential function, 2 to the x plus 1 is bigger than 2 to the x plus 2 to the x. So here we have two additions. So if we make the exponent 1 bigger, then clearly we have this estimate. And this is the same as 2 index n plus 2k plus 1 minus 1. So we see by some sort of simple induction you get this one. Now the next lemma is maybe of general interest. Lemma 4. And so let alpha be at least as big as omega to the omega, and m element of 2 to the h alpha of m, h alpha of m plus 1 minus 1. Then we have that the function which shows up in the phase transitions, the specific function is always bounded by the rightmost endpoint. And this is holds for all I less than equal to m. So for all i's not in this interval, but in the interval of points before this number. Okay, proof. And we have seen the picture of the proof already before in the lecture. We have a function which grows like this. And what we have to do, first we have to see that the function is monotone on these intervals. We only have to care about these exponents here. Then one sees they are basically weakly increasing. So what one has to show, one has only to care that this last one here has to be bounded by some point here to the right. One has to figure out where this is going to happen. And here is the corresponding bound. Now, coming back to the proof, we make a case distinction. Case A, claim, no, let's say, consider I be the interval from 0 to h alpha m minus 1. So we split the predecessors of m into the part h alpha m up to this number and the part to the left. And this here is the part to the left. And then the claim is that log 2 of h alpha inverse of I is bounded by log 2 and minus 2 of h alpha of m. Call this property star. Well, proof by verification. If I is in the beginning, so it's bounded by h alpha of 0, then log 2 h alpha inverse of I. This is just I because this function inverse here gives 0. This is of course bounded by h alpha of 0, bounded by log 2 of m minus 1 h alpha of m, since alpha is at least as big as omega to the omega. Well, we assume that m here, just to avoid pitfalls, maybe m is at least as big as 2, then there's no discussion. So that's fine. So this is by lemma 1. Okay, next one is h alpha of L is less than equal to I, strictly smaller than h alpha L plus 1 minus 1. So what we do is we split this interval into smaller intervals. And we make a gain case distinction. If you're in the rightmost interval, if L is equal to m minus 1, then what? Then log 2 of h alpha inverse of I is equal to log 2 of m mm, m minus 1. So h alpha inverse in this interval gives L, which is m minus 1, which is equal, this h alpha m minus 1 bounded by log 2 of m minus 1 of h alpha of m. So that's fine. If L is smaller than m minus 1, then there's a situation that we have to compare those ones with the last one. What do we do? Then log 2 of h alpha inverse of I bounded by log 2 of L of I bounded by log 2 of L of h alpha L plus 1 minus 1, the rightmost endpoint. Now I claim that this is bounded by log 2 m minus 1 h alpha of m. Here one has to be careful because L is smaller than this number. So this function here goes quicker than this function here. On the other hand, this function here is much, much slower than this function here. And this is what is going to happen. Namely, we have this is true because we have what? H alpha of L plus 1 is bounded by log 2 to the m minus 1 minus L of h alpha of m by lemma 1. Because h alpha of m is at least as big as 2 to the h alpha of m minus 1, at least as big as 2 to the 2 of h alpha m minus 2, etc., until we hit this number. Since alpha is at least as big as omega to the omega. Okay, now what are we going to show? We are going to show this property here. We have shown this one, but yeah, that's fine. Okay, we have this property. Now, we have shown this one. Okay. Further, if we now have log 2 minus 1 h alpha of m, this is bounded by log 2 of m which is the same as log 2 of h alpha inverse of m, of capital M. This is a small m, because log 2 of m bigger than log 2 of 2 to the h alpha of m, which is h alpha of m. So we get here one extra log. And the extra log allows to majorize by log 2 of m, log 2 of m minus 1. We need this m is at least as big as the exponential of this one. Okay, and then we see for these i's, we have this property. We have here majorized all these elements by the corresponding right one. Now what's left is b. I is in h alpha of m, and capital M. Then we have that log 2 of h alpha inverse of I, bounded by log 2 m of I, bounded by log 2 of h alpha inverse of m of m. H by a simple monotonicity. So in all cases, if I is in this interval, or if I is in this interval, always this is the upper bound. And this works quite generally. Now comes last technical lemma, lemma 5, namely the maximal coefficient of CKM is strictly bounded by K. Proof by induction on M. M is equal to 0, when Ck of M is 0, then the maximal coefficient of Ck of M is 0, less than equal, strictly smaller than K. We assume K is at least as big as 2. Now, assume what? That M is K to the R times P plus Q, where P is smaller than K, Q is smaller than K to the R, and M is smaller than K to the R plus 1. Then the maximal coefficient of CK of M is the maximal coefficient of omega to the CK of R times P plus CK of Q. We know that this is a normal form, so this is bounded by the maximum, the maximal coefficient of CK of R, P, and CK of Q. It's smaller than K by induction hypothesis, here too, and this is smaller than K by this assumption here. So this is smaller than K, and the lemma is shown. Okay, now we have everything together. And let us now consider the Goodstein sequence. For function f of x is function f alpha of x, which is the maximum taken over I less than equal to x. Log 2 h alpha inverse of I, where this is rounded to a natural number Doesn't matter that much. Okay. Now consider the Goodstein sequence. Let M be given. Now I have to write down a bound for the length of the Goodstein sequence. So let M be equal to H alpha, let's say of H omega to the alpha plus 1 of M. So for this alpha here and for this M here, I write down this bound here, which is that one. Okay. Consider the Goodstein process. M is equal to M0. This goes to M1, goes to M. Finally, read a number, say M tilde of M, where M tilde of M is the first place, least I, such that M of I is 0. Now, technically, we have to plug in here these notations to say that this is Goodstein sequence with respect to F, where F is equal to F alpha. Okay, now assume that number M is smaller than M tilde of M. And we have to derive a contradiction. So what we are showing is, the claim is that M is at least as big as M tilde of M. And now this number here, the function H alpha, the function H omega to the alpha plus 1, they are both provably total in arithmetic, so the composition exists and M is a well-defined value. Okay, now assume that this M is small. What do we obtain? Well, first of all, let O of ML be as usual, psi f of L plus 2 of ML f. Then, now here using the monotonicity of f, we can show that OM0 bigger than OM M tilde of M, which is 0 for the first time. And these are the MFs. Now let alpha I be OMF of I. Then what? Alpha 0 is bigger than alpha M. And now we assume here this one. So we assume that this sequence goes further. But what we do is we just forget about this part. We only look at this part. Now, what do we know? OM0 is C2 of M smaller than C2 of 2 index M, which is omega M. So what we see here, omega M is bigger than this number. Okay. Now comes the magic. We find number well, I make M slightly bigger. I don't want to have that M is this number. I want M is 2 index this number. Anyway, it doesn't matter that much. The hyperexponential function is also provably total in arithmetic because it's basically bounded by to the function h omega square, or no, h omega 3. H omega square is the exponential function, and then h omega 3 is the super exponential function. Anyway, what do we find? We find m is bounded by the number of beta less than omega m. So it's the maximal coefficient of beta is bounded by, and we have to be careful. Well, here we have the function values given by this function, and the maximal coefficient are bounded by these numbers. So the maximal coefficients in this sequence here is bounded by log 2 of h alpha inverse of m of m. Now we have to be careful here, because the f function was not strictly monotone, but by choosing the right m, so what do we have? We have h alpha of h omega to the alpha plus 1 of m is smaller than 2 index h alpha h omega to the alpha plus 1 of m. This is bounded by h alpha h omega to the alpha plus 1 of m plus 1. So this means we are in the right interval to apply our last lemma, namely that this term here bounds the values of the f functions for all the terms showing up over here. So these numbers here are bigger than the log 2 of h alpha inverse of I for I less than equal to m. Okay, so we have this. Now comes the next magical step, namely this is the same as we take omega m and replace omega by the value. Here's, I forgot, there's some plus 2 involved, but it's not a big issue. I can plug in this number for omega. Yeah. Hi. I'm making a Zoom, but I'll come back to you. So we get this estimate, and so what do we obtain? Well, what is h alpha inverse of m? So it's 2h alpha of h omega to the alpha plus 1 m. It's the same as, well, we are in this interval. So that's the same as h omega to the alpha plus 1 of m. So that's the same as we take the function log 2 of h omega to the alpha plus 1 of m plus 2. Then we take a tower of height m divided to number 1. So this is bounded by m is 2 index h alpha of h omega to the alpha plus 1 of m. Now if I do what? If I apply the log function h omega alpha plus 1 many times here, then I obtain here 2 index. I take the original function. And then I have to subtract h omega to the alpha plus 1 of m many times. Because for this I do the iteration over here. And Then I have here m. And then I have plus 2 of m. Now this plus 2 is a bit of nuisance, so I make this term bigger. And then I have here an m. Now apply my rule, which I showed in the beginning, 2n of k of 1, bounded by 2n plus 2k minus 1. So this thing here is bounded by 2 index h alpha, h omega to the alpha plus 1 of m minus h omega to the alpha plus 1 of m plus 2m minus 1 plus 1. And then at the final end, we'll see what's going on. Namely, this term here, much bigger than this term. So this is strictly smaller than 2 index h alpha of h omega to the alpha plus 1 of m. And this leads to a contradiction because this number here is equal to 2 index h alpha h omega to the alpha plus 1 of m. So m is strictly smaller than m. So this is impossible. Yeah, so summary. The length of the Goodstein sequence starting with m with respect to growth rate function f alpha is bounded by the provably recursive function m goes to 2h alpha of h omega to the alpha plus 1 of m. And this ends the lecture.